Hey everybody, welcome back. I think this is maybe our fifth video. And we're moving on. We're on section 2.3. And the objectives for this section are to describe continuity, find different types of discontinuity, and then get a good understanding of the intermediate value theorem. So here's my joke for today. I hope you enjoyed it. Okay, so let's start. What does it mean for a function to be continuous? When we were studying Algebra 2, we talked about a function being continuous if you did not have to lift up your pencil when drawing it. So let's talk about your heart rate. Let's say you start by sitting on the couch. Let's say these go by 20, so that's 20, 40. And I have a pretty low resting heart rate. Don't ask me why. So my heart rate would start here. Then if I got up and started walking around, it might go up to 60. Then let's say I got on the spinning bike, it might go up to maybe like 150. And then let's say I just stayed on the spinning bike for that amount of time. So that would be an example of a continuous function. If my heart rate was 60 and then and then a few minutes later, my heart rate was up to 80. I know that my heart rate during that amount of time were all the values in between 60 and 80. So at some point, my heart rate was 61, was 62, 64, 75 until it got up to 80. It was all those values in between 60 and 80. It didn't just do an abrupt jump to 80. That's true like of height as you grow. Maybe at your doctor's appointment, you were 5'8", and then the next year you were 5'10". Well, you didn't just go from 5'8" to 5'10". You were all those heights in between over that year-long period. So that's continuous. A parking meter is not continuous. So let's say it is $1 for every hour. So obviously that's not Cherry Creek. They're a lot more than that. So it would look like this. Then at 1 hour, it's going to jump up to $2. And then the second it hits the second hour, you're paying $3. Okay, so that function looks like this. And this is called the greatest integer function. And we actually have a symbol for that, and it looks like this. Okay, so this function's continuous. This function is obviously not continuous because to draw it, you had to lift your pencil up. The other way you know this is not continuous is the limit from the left does not equal the limit from the right. So for example, in this case, f of 1 is equal to 2, but the limit as x approaches 1 of this function, we'll go from the left-hand side, is 1, but the limit as x approaches 1 from the right-hand side is equal to 2. So therefore, this function is not continuous. So there's some examples of a continuous function and a non-continuous function. Okay, let's look at another example. You can define continuity at an interior point and also just simply at an endpoint. So let's do an example of this first. Okay, so we're going to take a look at this drawing right here to help us. Okay, so let's take a look at f of negative 2. So that's over here. So does f of negative 2 exist? Yes. And f of negative 2 is actually equal to 0. Does the limit exist? It doesn't. The limit from the left is 2. The limit from the right is 0. So does the limit equal the value of the function? No. So therefore it's not continuous. Okay, let's try f of 0. So that's right here. So f of 0 is equal to negative 2. So I don't know why I did a parentheses there. And the limit from the left is -2, and the limit from the right is -2. So yes, it exists. And the limit is equal to the limit as x approaches 0 of f of x is equal to -2. Does the limit equal the value? These two are the same, so yes. So therefore it's continuous. Okay, you try f of 2 and then we'll talk about it. So you look at f of 2 and then we're going to discuss it. Okay, so f of 2 is actually equal to 0 right there. So f of 2 is equal to 0. The limit does not exist. The limit from the left is 0. The limit from the right is 4. So the limit does not exist. Okay, so therefore the limit does not equal the value of the function, so it's not continuous, because the answer to that question is no. Okay, we can also describe continuity at an endpoint. At an endpoint, so that's for an interior point. For an endpoint, a function y equals f of x is continuous at a left endpoint if the value is defined there. So let's take a look at this. So for f of -6, we have an open circle. It's hard to see, but we have an open circle right there. So if we think about this, f of -6 does not exist, okay? And the limit as as x approaches -6 from the right-hand side is equal to 2, but because these two values are not the same, it is not continuous at that value. Another way to kind of think about this, maybe logically or with some intuition, is because we can't ever get to -6, we could get infinitely close to that. So for example, we could approach this at -5.9, -5.99, -5.999, -5, and that could go on forever. So we will never get to -6. So that shows us that we can't ever reach that, so that is a discontinuity. Okay? All right, let's look at f of 6. F of 6 is equal to 0. The limit as x approaches 6 from the left-hand side, so it's the only direction we can approach it from, is also equal to 0. So therefore, it's continuous. So if you have an open circle at an endpoint, it's not going to be continuous there. If you have a closed circle at an endpoint, that would be continuous because you can actually reach that point. Okay? All right, moving on. So that's continuity at an interior point, which is what we worked up here, and this is continuity at an exterior point. Oh, okay, and here's the definition. Hopefully these are in your notes about an endpoint. Is it continuous if the value equals the limit? Okay, so we're going to talk about some conditions that exist which cause a graph to be not continuous at a specific value. So first we're going to talk about a removable discontinuity. A removable discontinuity is a hole. Okay, so I'm actually going to start with f of x is equal to, let's do, whoops, didn't mean to do that bracket, sorry. Let's do x minus 1 squared divided by x minus 1. Okay, I could simplify that to be x minus 1, these two, if I divide these two. However, x can still not equal 1 because in my original function, that would cause the denominator to equal 0. So if I were to draw this function, it would look like this. But I'm going to just pause right here, and I'm going to show you an example with the calculator. Let me go back. Here's our function right here, x minus 1 squared over x minus 1. And when I look at it, it looks like a perfectly normal line, but it's a little bit misleading. I'm going to look at the table. So on the Inspire, if you hit Control T, you can see the table. And I can see that at 1, my function is actually undefined there. That's what that hashtag UN undefined. So the graph doesn't show it, but really there is a hole at when x equals 1. So to more accurately draw our graph, we should put an open circle at 1. Well, that doesn't really look very open, does it? Let me try and make it look a little bit better. I'm going to do an open circle. Okay, so that's a removable discontinuity, and we know that if we were to draw it, we have to lift our pencil up in order to draw that line. The other way we know that there's a discontinuity is the limit from the left is equal to 0 at x equals 1. The limit from the right is equal to 0, but f of 1 is undefined. Okay? So that's a removable discontinuity. Okay? Now, a function could have a removable discontinuity, but then it could be defined. And this is called a piecewise function. So let's say we have x minus 1 squared over x minus 1. Okay? And this is going to be for all the times when x does not equal 1. But we could go ahead and fill in the hole and say when x equals 1, f of x is equal to 0. So what that would look like graphically is our line, and it has an open circle. So this is the first part of the piecewise function. But then the second part of the piecewise function fills in that hole. So actually this is now continuous. So the limit from the left is 0 at x equals 1, the limit from the right is 0 at x equals 1, and then f of 1 is equal to 0. So the limit is equal to the value, and therefore this is continuous. And this function is not continuous. Okay, the next type of discontinuity we can have is called a jump discontinuity, and those are those step functions that we just drew. So those look like this. And that's called an integer greatest integer function. It looks like this symbolically. And you can type this into your calculator by just typing in the letters int and then x in parentheses, and you can get that greatest integer function. This graph is a little bit misleading because there will be an open circle here at each of those values. Okay. So that's called a jump discontinuity, and that's kind of obvious because you actually have to jump up to draw the next part of the graph. Okay, an infinite discontinuity would look like this. This is what 1 over x squared looks like, and there's an infinite discontinuity at x equals 0. An infinite discontinuity is also known as an asymptote. Okay, and then finally, an oscillating discontinuity. Let's look at the graph of sine of 1 over x. And I've already loaded that in, and it looks like this. And let me go ahead and zoom in. And if I keep zooming in, you can see as I get closer and closer to 0, that has an oscillating behavior. So another discontinuity can be an oscillating behavior. So there's actually a discontinuity at 0. So this function looks like this, and then it goes crazy in the middle. Okay, maybe not exactly like that. Okay, so that's our video for today, talking about continuity and some specific types of discontinuity, and also talking about continuities at an interior point and an exterior point. Okay, thanks for watching.